What does a $500 racing drone have in common with the most advanced weapons in modern warfare? On May 19, 2025, a Ukrainian-built quadcopter launched from a concealed bunker on Snake Island, crossing 35 kilometers of open Black Sea with a single objective: destroy the NEVA radar system on Boyco Tower Alpha, a Russian-held gas platform that monitored strategic waters and restricted Ukrainian movement. But this was only the first strike. Moments after the quadcopter's mission, a second, far larger unmanned vessel was already en route, signaling a coordinated attack that would test the limits of Russian defenses. Stick around to see how this double drone strategy redefined naval combat, and how a simple racing drone became a weapon that challenged established military doctrine. On the morning of May 19, 2025, a small quadcopter assembled in a Kiev workshop prepared for a mission that would underscore a new era in military technology. Built on a standard 10-inch racing drone frame and sourced from readily available Chinese components, this device was never intended for combat. Yet, with a total cost under $500, less than the price of an annual Netflix subscription, it emerged as a tool capable of altering the balance of power across the Black Sea. The transformation from hobbyist gadget to weapon began with the adaptation of its core structure. Engineers replaced the usual lightweight racing accessories with a custom explosive payload: 3 kilograms of high explosives, zip-tied directly to the drone's underside. This modification did not require advanced military manufacturing or classified materials. Instead, it demonstrated how commercial, off-the-shelf technology could be rapidly converted for battlefield use, enabling a nation under siege to respond with speed and flexibility. What set this FPV, first-person view, drone apart from traditional military UAVs was not only its cost, but its method of operation. Rather than relying on GPS guidance or pre-programmed flight paths, methods susceptible to jamming and electronic warfare, the FPV system transmitted an analog video feed straight to the operator's goggles. This real-time connection allowed the pilot to see exactly what the drone saw, making split-second decisions and course corrections as necessary. The analog system also proved more resistant to Russian jamming efforts, giving the Ukrainian operator a tactical edge over conventional GPS-dependent systems. The operator, known by the call sign Soil, faced the challenge of guiding the drone across 35 kilometers of hostile airspace. From his concealed position on Snake Island, he piloted the quadcopter with precision, maintaining constant visual contact through the analog video feed. The mission demanded a level of focus and adaptability that only a human pilot could provide. Unlike larger, more complex UAVs equipped with redundant systems and automated controls, this drone depended entirely on Soil's judgment and manual input. To evade Russian detection, the drone maintained a flight ceiling below 50 meters and followed an unpredictable, zigzagging path. This low-altitude, erratic flight profile exploited gaps in Russian radar coverage, which was optimized for tracking larger, higher-flying threats. The combination of small size, low radar cross-section, and unpredictable movement made the drone difficult to detect and even harder to intercept. Russian defenses, designed for conventional aerial threats, were ill-equipped to track and respond to such a small, agile target. Battery endurance posed another critical constraint. At a cruising speed of 65 km per hour while carrying 3 kilograms of explosives, the drone's battery life was pushed to its limit over the 45-minute flight. This required meticulous planning to ensure the drone could reach its target and deliver its payload with enough power remaining for final course corrections. Each aspect of the mission, from payload weight to flight path, was calculated to maximize the likelihood of success while minimizing exposure to enemy defenses. The simplicity and affordability of the FPV drone did not diminish its impact. In fact, these qualities allowed for rapid deployment and a degree of expendability that traditional military assets could not match. The Ukrainian approach did not seek to replace advanced UAVs, but to complement them, forcing Russian forces to expend significant resources countering threats that cost a fraction of their own defensive systems. The willingness to risk a $500 platform for a high-value target shifted the calculus of modern warfare, introducing a new kind of asymmetry. Yet, technological improvisation alone was not enough. The success of the mission depended on the operator's ability to exploit both the strengths of the FPV system and the vulnerabilities of Russian defenses. Soil's decisions to fly low, to zigzag, to approach the target with minimal warning were as crucial as the hardware itself. The drone's arrival at Boyco Tower Alpha, undetected by the NEVA radar system, underscored the limitations of even the most advanced surveillance equipment when faced with an unconventional threat. The stage was now set for a confrontation between a $500 device and one of Russia's most critical surveillance assets. The next moments would test the NEVA radar's ability to defend itself against a threat it was never designed to face. On Boyco Tower Alpha, the NEVA radar system stood as a sentinel over the Black Sea, its 35 GHz antenna sweeping the horizon with a 45-kilometer reach. Capable of tracking 200 targets simultaneously, it formed the backbone of Russian surveillance and targeting operations in the region. Its presence gave Russian forces the ability to monitor both surface vessels and aircraft, controlling a strategic corridor and restricting Ukrainian movements. For Ukraine, neutralizing this system was a priority. Removing it would mean regaining operational freedom in contested waters. The NEVA's design reflected Cold War priorities: resilience against harsh maritime conditions and electronic jamming. Its electronics were shielded, and its rotating antenna housed in lightweight aluminum sheeting, effective at resisting salt spray and rain. Yet these protective measures were never intended to withstand a direct explosive attack. The system's engineers had not anticipated the threat posed by a small, low-flying drone carrying a precisely targeted payload. For the Ukrainian operator, Soil, the mission demanded both precision and nerve. The FPV drone's objective was clear: strike the junction where the antenna's rotating assembly met its control unit. This was the radar's most vulnerable point, a critical node linking the transmitters, receivers, and waveguide systems that enabled the NEVA to function. Disabling this section would render the entire system inoperable. Through the analog video feed, Soil guided the drone with real-time adjustments, exploiting the FPV system's unique advantage: the ability to target the radar's weak spot with accuracy that pre-programmed coordinates could not match. The approach relied on stealth and deception. By flying under 50 meters and following a zigzag path, the drone remained below the radar horizon and masked its movement against the sea's background clutter. Russian detection systems, optimized for larger, more predictable threats, struggled to distinguish the drone from environmental noise. The erratic flight pattern also complicated any attempts by Russian personnel to visually track or target the drone. Traveling at 65 kilometers per hour, the drone's small frame and low altitude left defenders with minimal warning. Seconds before impact, Russian personnel finally spotted the approaching drone. A lone individual on Boyco Tower Alpha raised a rifle and fired. But with less than 10 seconds until impact, the shot had no chance to stop the drone. The platform's defenders were left with only a fleeting opportunity to react before the attack reached its conclusion. At 9:20, the drone struck the NEVA radar's antenna assembly. The 3-kilogram explosive payload detonated instantly, directing its force into the radar's most delicate components. The blast severed the antenna from its base, shredded the waveguide system, and destroyed the transmitter and receiver modules. Fragments of aluminum and steel scattered across the platform, leaving the radar's core irreparably damaged. The NEVA, once capable of orchestrating surveillance and targeting across the northwest Black Sea, was reduced to a collection of scorched, inert parts. The focused nature of the strike underscored the vulnerability of even robust military systems to targeted, low-cost attacks. The NEVA's housing, effective against weather and electronic warfare, provided no protection against a direct kinetic threat. This gap in the system's defenses revealed a fundamental flaw. Traditional engineering assumptions had not kept pace with the tactics and technologies of modern drone warfare. The aftermath was immediate and significant. With the NEVA radar disabled, Russian forces lost a crucial surveillance asset, temporarily blinding their operations in a critical maritime zone. For Ukrainian forces, the removal of this obstacle opened new possibilities for movement and maneuver in the Black Sea, shifting the local balance of power. Yet, the destruction of the NEVA radar was only the beginning. As smoke drifted from the ruined antenna, the defenders of Boyco Tower faced a new and far more formidable threat approaching across the water, one designed not just to blind, but to obliterate. The Sea Baby was purpose-built by the SBU for a single objective: destruction. Measuring 6 meters in length, this unmanned surface vessel carried a payload of 1,000 kilograms of military-grade explosives. Its design marked a departure from improvised systems, representing a deliberate advancement in Ukraine's maritime warfare capabilities. With a low-profile hull and grey paint, the Sea Baby blended with the sea's surface, reducing its visibility to both aerial and surface patrols. The vessel's appearance echoed a high-speed patrol craft, but beneath this exterior was a weapon engineered for maximum effect against hardened maritime targets. The Sea Baby's destructive potential came from its warhead configuration. Multiple shaped charges arranged around the bow were designed to detonate in a sympathetic sequence. This arrangement focused the explosive force, ensuring that the primary blast would trigger secondary charges in rapid succession. The resulting explosion generated temperatures exceeding 3,000 degrees Celsius, capable of melting steel and pulverizing reinforced concrete. The explosive mixture, RDX and TNT, was selected for its ability to deliver both a powerful shockwave and sustained thermal energy, maximizing damage against structural supports. Propulsion and survivability were central to the Sea Baby's mission profile. Twin 200 horsepower water jets cut acoustic and radar signatures while pushing the vessel to 90 kilometers per hour, even if one engine failed. This combination of speed and stealth complicated detection by Russian naval forces. The water jets minimized underwater noise, making it harder for sonar systems to track the vessel. The Sea Baby's hull was engineered to ride low in the water, further reducing its radar cross-section and allowing it to take advantage of sea conditions and shadows cast by larger structures. Navigation relied on a combination of GPS, inertial guidance, and real-time satellite communication. Human operators maintained control through encrypted satellite links, with redundant frequencies ready if Russian electronic warfare teams attempted to jam the signal. This ensured the Sea Baby could receive course corrections and targeting updates throughout its journey. The operators had access to detailed intelligence about the Boyco Tower's layout, including the precise location of storage tanks, support columns, and living quarters. This intelligence allowed them to select the approach vector and impact point that would cause the greatest structural damage. The mission required careful planning. The Boyco Tower was a stationary, well-mapped target, allowing Ukrainian planners to calculate the optimal route and timing. The Sea Baby's approach vector was chosen to minimize exposure to Russian patrols and defensive fire, exploiting gaps in surveillance and leveraging the vessel's speed to reduce reaction time. The vessel's electro-optical camera package provided a real-time video feed, allowing operators to lock onto the platform's main support structure, the junction between the drilling platform and the accommodation block. Destroying this point would threaten the integrity of the entire installation. Unlike the smaller FPV drone, which relied on erratic movement and low altitude to evade detection, the Sea Baby's advantage was its combination of speed, stealth, and precision targeting. The vessel's kinetic energy at maximum velocity transformed it into a 6-ton projectile. The impact, coupled with the detonation of 1,000 kilograms of explosives, was calculated to overwhelm any structural defenses. The shaped charges would focus the blast against the critical junction, exploiting the weakest link in the platform's design. As the Sea Baby closed the final distance, every aspect of its design and operation came into focus. The vessel's systems maintained a lock on the target, operators monitored telemetry and video feeds, and the Boyco Tower's defenders scrambled to respond. The attack was the culmination of months of intelligence gathering, engineering, and tactical planning. The Sea Baby was not simply a demonstration of technical capability. It was a signal that unmanned systems could achieve strategic effects once reserved for manned operations. The stage was set for the decisive moment. The Sea Baby's final approach would test the limits of both its engineering and the defenders' ability to respond. What happened next would show the true consequences of bringing 1 ton of explosives into direct contact with a platform's weakest structural point. Toppling Boyco Tower was not simply a matter of delivering a massive payload, but executing a calculated strike at the platform's most vulnerable junction. Ukrainian planners had identified the structural link between the drilling platform and the accommodation block as the critical point. This section, engineered for operational loads and environmental stress, was never designed to absorb the impact of a purpose-built unmanned vessel moving at high speed with a ton of explosives. As the Sea Baby entered its final approach, its systems maintained a lock on the target, updating operators in real time. The vessel accelerated to nearly 90 kilometers per hour, guided by electro-optical targeting to the precise spot where a direct hit would trigger the greatest structural failure. On the platform, Russian personnel reacted with urgency, shouting, moving toward defensive positions, but the timeline had collapsed to seconds. The platform's defenders had no effective countermeasure for a threat arriving with this speed and precision. The collision was immediate and overwhelming. The Sea Baby struck the main support junction, and the shaped charges arranged around its bow detonated in a tightly coordinated sequence. The initial explosion delivered a focused shockwave, and sympathetic detonations followed, amplifying the force into the heart of the platform's foundation. Temperatures at the blast site surged beyond 3,500 degrees Celsius, liquefying steel and pulverizing reinforced concrete. The kinetic energy of the impact, combined with the shaped charges engineering, ensured that the structural supports failed in rapid succession. Within the first second, the accommodation block, where Russian personnel were housed, disintegrated. Prefabricated walls and floors vaporized in the sustained fireball, leaving no possibility of survival for anyone inside. The destruction of the living quarters was instantaneous, erasing the platform's command and control center in a single moment. The force of the blast radiated outward, severing key support columns and destabilizing the upper decks. The secondary effects compounded the destruction. Storage facilities packed with equipment and supplies ignited, their contents fueling a series of cascading blasts. Fuel tanks holding diesel ruptured and spilled into the growing inferno, feeding columns of fire that soared hundreds of meters above the wreckage. The sequence of explosions and fires swept through the platform, consuming each section in turn and ensuring that the structure's collapse was both total and irreversible. In less than 5 minutes, the Boyco Tower's upper structure had collapsed into the Black Sea. The interconnected decks, accommodation blocks, and operational equipment were reduced to twisted steel and shattered concrete, much of it sinking beneath the surface. The remnants that remained above water were unstable and engulfed in flames, marking the end of a platform that had served as a critical node for Russian military operations in the region. Survivors of the initial blast found themselves stranded on unstable debris, with no hope of immediate rescue. Fires continued to burn across the remains, and the violence of the collapse had scattered lifeboats beyond reach. The few who managed to escape into the water faced hazardous conditions: diesel slicks, burning wreckage, and the absence of any safe haven. With helicopter evacuation rendered impossible by the ongoing fires and distance from Russian bases, the aftermath for those left behind was grim and uncertain. 2 hours after the strike, Ukrainian satellites passed overhead, capturing imagery of the aftermath. The Boyco Tower was gone, replaced by burning wreckage and oil slicks drifting on the surface. The NEVA radar, already destroyed earlier by the FPV drone, was now joined by the total loss of the platform itself. The images provided undeniable evidence. The operation had succeeded in neutralizing a key Russian surveillance and logistics asset, leaving nothing recoverable for immediate reuse. By demolishing Boyco Tower, Ukraine shattered Russia's surveillance keystone in the northwestern Black Sea. The Boyco Tower operation demonstrated how accessible drone technology can undermine traditional military dominance at sea. A compact FPV drone and an unmanned surface vessel exposed vulnerabilities in entrenched defences, proving that asymmetric tactics and rapid adaptation can surpass expensive, established systems. As drone warfare evolves, navies worldwide must reconsider their strategies and invest in new countermeasures to protect critical assets from these emerging threats. If you found this breakdown illuminating, hit subscribe to stay ahead of the latest in drone warfare. How do you think navies will adapt to these new low-cost, high-impact threats? Let us know in the comments below.